Good evening, everyone. My name is Kostas Stasis, and on behalf of the Hellenic Astronomical Society, I would like to introduce our speaker today, uh, who is Professor Vasileios Paschalidis. It is my distinct pleasure actually introducing him today, since he actually comes from my alma mater, and he's an old friend. Vasileios got his undergraduate degree, his bachelor's degree from the Aristotle University of Thessaloniki in 2003. And then he moved to the University of Chicago, where he obtained his PhD in 2008. It was actually during this period when we actually met in Chicago, right? Some time ago. Then he had his first postdoctoral appointment at the University of Illinois at Urbana-Champaign, which is my other alma mater. So we have a lot of things in common. And that was from 2008 to 2013. And then he got a prestigious fellowship for another year in 2014 in Illinois. When he decided then that the weather was terrible, so he moved to the East Coast at Princeton University, where he spent another 3 years from 2014 to 2017. And then he got desperate for more hot weather, I suppose, and he moved to Arizona, where he is now an assistant professor in physics and astronomy since 2017. His research interests are related to numerical simulations in general relativity, and his work is very much relevant to the new window that is opening up due to the gravitational wave detections, the recent developments. So without further ado, Vasily, the floor is yours.
Thank you very much, Costa, for the kind introduction. And let me say that when Costas went to Chicago, I was a student in Chicago, and then I went to the University of Illinois as a postdoc. So Costas was a postdoc at the University of Chicago. So we switched institutions at the time. And interestingly, I remember when I went to Illinois, Charles Gami had made this interesting note that there must be some new conservation law at the University of Illinois. And he said it's the number of Greek students or postdocs at the University of Illinois. So it seems like there's always one or two students that are there, and then we always end up somehow at the University of Illinois. Anyway, so let me share my screen. Okay. So, all right. So, as the title suggests, I'll be talking today about probing fundamental physics through a synergy of numerical relativity with gravitational wave observations. This is the new field of gravitational wave astronomy and how using numerical simulations in general relativity can help us understand and interpret these gravitational wave observations. So here's a quick outline of the talk. First, I'm going to introduce some things just to make sure that we're all on the same page, mention what a gravitational wave is, how gravitational wave detection works, why numerical relativity is important for gravitational wave detection. And I'm going to try to bring you up to speed in case you haven't really seen what the latest developments in the gravitational wave detections are. I'm going to tell you a little bit about what LIGO and Virgo have detected so far. Then I will switch to the next two parts in the talk. Will be more about what we have learned from these detections and how numerical relativity has actually helped in learning about the nuclear equation of state when it comes to binary neutron stars. And if time permits, I will also tell you some recent work that I've been doing on binary black holes and how we can use binary black holes to constrain what I say here, U1 charge, and you can think of it as electric charge, but it's much more than that, as I will explain, hopefully, when I get to that point. Would also like to say that if at any time you have any questions during the talk, feel free to just unmute yourself and ask the question. I don't want necessarily for this talk to be just a monologue. So if we can create a dialogue, that will be even more pleasant. My primary goal is to just for everyone to enjoy this and learn something new along the way.
Well, Vasily, may I interrupt? Could
Yes.
you make it a full screen presentation?
Yes, it is a full screen presentation. You cannot see it?
We can still see your toolbars. I don't know.
Oh. Oh, you mean down here?
Yes, and
Oh,
up there.
but this, yeah, I don't think this is gonna go away, to be honest. I think this is a Linux thing.
Okay,
But let me, oh wait, it actually did go away. Okay.
there you go. Okay, perfect. Thank you.
I had to click on the screen. Okay. All right, so what is a gravitational wave? Gravitational waves are perturbations in the gravitational field that propagate at the speed of light. To generate a gravitational wave, just like in electromagnetism, if you move a charge very rapidly, you generate an electromagnetic wave. Similarly, in gravity, if you move a massive body very rapidly, you generate a gravitational wave. And so this is what this figure depicts here. It shows two stars that are dancing around each other, just move very, very fast near the speed of light, and they generate these ripples that are depicted here, which are the gravitational waves that propagate far away, and these are what we're trying to detect here on Earth. Now, gravitational waves, just like all waves, have several properties. They carry energy, and the energy is actually moved from the orbit of the binary. And this leads the orbit of the binary to shrink with time. And so that's what allows the binary to eventually collide. And it's through that collision that we hope to learn many, many new things about fundamental physics and astrophysics, of course. So one of the important properties of gravitational waves is that they're polarized, just like other waves as well. And what they do is they squeeze and stretch space in perpendicular directions. And they change the distance between freely falling objects. So if there's no force acting on this ring of particles that is shown here on this cartoon here, and you imagine that there's a gravitational wave that's going into the screen, then then it's going to make it oscillate in this particular pattern that is shown here. This is known as the plus polarization because it makes the ring oscillate in this plus direction. And the fractional distance between the maximum fractional distance that you can see between two different particles, which is delta L over L, is essentially the amplitude of the gravitational wave. So that's how we can find out what the gravitational wave amplitude is if we just measure the distances between different particles. There's another polarization the gravitational waves have in general relativity, which is the same as this, but rotated by 45 degrees, and that's called the cross polarization of gravitational waves. And so really it's this polarization that gravitational waves have that gravitational wave detectors take into take advantage of, and they try to make a detection. So this is the cartoon of a LIGO interferometer or a LIGO gravitational wave detector. There's a laser beam that goes into a beam splitter, and then half of it goes into this upper arm, and the other half goes through this right arm here. And there's much more that goes on in here, but if there's no gravitational wave, everything is set such that when the beams return back and they go out here, where we try to see what the interference pattern is, that the two waves that are coming from the different arms, they completely cancel each other. So they actually are indestructive interference. But if there's a gravitational wave coming by, then what will happen, as I said, it's going to squeeze one direction and it's going to expand the other direction. So the arms, of course, this is severely exaggerated compared to what happens in reality, but the arms are going to be changing the distances in different ways. And the path is going to change. The path that the light travels changes, and then it will shift the interference pattern. And so it will go from destructive interference to well, not really constructive interference, but going from seeing nothing to seeing something tiny. And so that's what really the gravitational wave detectors do, and that's the principle in which they operate. Okay, so the amplitude of the gravitational wave. So if we want to understand what kind of sources we should be looking at, we need to look at how strong these gravitational waves are. And so we can estimate the amplitude of the gravitational wave, which is again related to the fractional change in the distance between freely falling objects. According to the quadruple formula, Einstein's quadruple formula, is proportional to the mass of the system that generates the gravitational wave and proportional to the velocity squared. C is the speed of light, G is Newton's constant of gravitation, and it's inversely proportional to the distance. So the further away something is, obviously, the weaker the gravitational wave is going to be. And so we can plug in some values in this formula to see what roughly the order of magnitude is for that gravitational wave amplitude. And if we plug in just a completely randomly chosen 3 solar masses that I have here, and a speed that is roughly close to the speed of light, and we place the object about 100 megaparsecs away from us, then the amplitude turns out to be about 10 to the minus 21st. Now, of course, to put this number in perspective, whether it's small or large, we have to see what kind of a fractional change in the distance between 2 particles it would cause. And so if we place 2 particles to be about 100 kilometers away, that means delta L for 10 to the minus 21 is going to be 10 to the minus 16 meters, which is smaller than the size of a proton. So really what gravitational wave detectors are trying to do is detect such tiny changes in distances smaller than the size of a proton. And the reason why this happens is not because gravitational waves are weak. In fact, gravitational waves are really among the most luminous things that we detect in the universe. And if we view them as explosions of energy within fractions of a second, they are far more luminous than any light that we observe from the most luminous light source that we observe in the universe. So the reason why it's so weak, it's actually because gravitational waves couple with matter very, very weakly. So that's why these changes in the distances are so tiny. And to understand really the sources that we have to look at and we'll have to look for, since we want to have as big mass as possible to maximize the gravitational wave amplitude, then we have to look at solar objects, stellar populations, solar mass objects. So, and at the same time, we also want to have things that travel near the speed of light. And if we take one of the most common sources in the universe, which are the binaries, then if we place 2 stars on a Keplerian orbit, the velocity of the Keplerian orbit is going to be given by root gm over the orbital separation. And we can solve this equation with respect to the orbital separation, and then plug in some values for the velocity and the mass of the system. And then if we say the velocity is about 1/3 of the speed of light, and again, we use 3 solar masses for the mass of the system, that means that the 2 objects have to be at most 50 kilometers apart. Okay, so that's really what we need. We need objects that are more massive than the sun, or about the same mass of the sun, but they have to fit within 50 kilometers. And to fit 2 objects within 50 kilometers, 2 objects, that means that the radius of each object has to be at most the orbital separation divided by 2, which is 25 kilometers. Okay, so these objects have to be very, very small, very compact. So the only way we can really have an object as big as the sun, which is 600,000 kilometers, we have to shrink it down to 25 kilometers at most to put it on an orbit that is going to be traveling near the speed of light and have 2 of them at the same time. And so the only objects that can do that we are aware of are black holes and neutron stars, which are the endpoints of stellar evolution. And this is why the holy grail of gravitational wave astronomy are black holes and neutron stars. That's what we really are interested in. And just in case there are any students who have not heard of what black holes and what neutron stars are, just very, very quick encyclopedic, I would say, description of the black holes and neutron stars. A black hole is a region of space-time where gravity is so strong that even light cannot escape. The surface of a black hole is known as the event horizon, And for a non-spinning black hole, it has a radius of 2 times g times the mass divided by c squared, which for a 10 solar mass black hole is about 30 kilometers. The event horizon of a black hole is a one-way membrane, which means that once you cross it, you cannot actually exit. That's it. You're trapped forever. And the black hole event horizon hides a physical singularity. You can easily understand, I guess, mathematically what a singularity is, but if you can't, just think of something blowing up, something becomes infinite. And there exist supermassive black holes, not just these stellar mass black holes of a few solar masses, like 10, 20 solar masses. There exist supermassive black holes that can be as massive as 10 to the 6 and to 10 to the 10 solar masses, which are being discovered at the centers of distant galaxies. And what about a neutron star? Neutron stars are the densest celestial objects that consist of normal matter. And by that, I mean neutrons, protons, electrons, plus some other maybe more exotic particles that may exist inside the interiors of neutron stars. The typical density of a neutron star is about 10 to the 14 grams per cubic centimeter, which means that if you take a teaspoon of matter of a neutron star, it would weigh here on Earth 1 billion tons. That is pretty much the weight of Mount Everest, only that this is not Mount Everest. This is Mount Denali. This is Mount Everest, in case you ever wondered what it looks like. And the typical neutron star mass is about 1.4 times the mass of the sun, and the typical size of a neutron star is about 10 kilometers, but it is uncertain because we do not understand the nuclear physics well enough at such high densities. And so that is one of the things that we hope to achieve with gravitational wave astronomy and numerical relativity simulations that I mentioned at the beginning of the talk. And just like black holes, neutron stars form after the death of a very massive evolved star. All right, so to summarize, the gravitational wave sources that we're after are binary black hole mergers in vacuum from stellar mass black holes to supermassive black holes to even extreme mass ratio inspirals, these EMRIs, which is a small object inspiraling to a very, very massive black hole. We're looking for binary neutron star mergers. We're looking for binary black hole neutron star mergers. But to do that, because these gravitational wave signals are very weak, and because we're trying to find changes in distances that are 10 to the minus 16 meters, we really need templates for detection. We need to know what we're looking for in the noise of the detector if we want to be able to find these gravitational wave signals. And one of the most reliable ways to build these templates is to solve the Einstein equations of general relativity. So there are multiple different methods for solving the Einstein equations in an approximate way. And obviously, this has worked very, very well. But if we want to be able to understand what happens near the last stages of a binary merger, we really need to solve the Einstein equations using supercomputers. And that's why the field of numerical relativity is very, very important for the success of the gravitational wave astronomy program. Okay, so let's look at the basic anatomy of a gravitational wave from a binary black hole, which is usually called a chirp signal. So this is a simulation that I ran. It solves the Einstein equations for two inspiraling black holes. So here on the left, you can see the two black holes in space and their orbit. And on the right, you can see the one of the polarization of the gravitational waves. What you see as time goes by, the distance between the two black holes shrinks. And as a result, the amplitude of the gravitational wave increases. And since the orbit shrinks, the black holes orbit faster and faster and faster. And so the frequency of the orbit also increases. And so that's why you see here that the distances between two different peaks decreases with time, which means that the frequency increases. And so eventually the two black holes merge, and you get this characteristic signal that is known as a chirp signal. We have increasing frequency and increasing amplitude as a function of time. And so this is really what LIGO is looking for in a gravitational wave data, in the gravitational wave data of the detector. All right. Now, of course, there are a lot of things that need to go into computing these kinds of waveforms. This is a very simple binary. It was actually spinning, but the spins were aligned with the orbital angular momentum. There can be spins, there can be orientation effects, which would lead to the precession of the orbit at the same time. Their mass ratio. If we have matter, the equation of state will leave an imprint on the gravitational waveform. And so all these things fold into this pretty much one-dimensional like time series that we detect. And what we want to do is actually invert this in order to be able to determine what are the parameters of the source that generated this particular wave. And so this can be done if we have sufficiently good templates. And that's why, again, we need numerical relativity. We need to be able to do these kinds of simulations that I showed here. Okay, so with the help of numerical relativity, LIGO and Virgo has actually calibrated a set of template banks for detecting gravitational wave signals from binary black holes and from binary neutron stars. And with that, they're doing an amazing job. Obviously, they're detecting multiple sources. So here's a summary of the detections that LIGO and Virgo had during the first two observing runs, observing run 1, 01, and observing run 2, 02, which in my opinion were maybe the most exciting ones, but we'll see what the third observing run is going to bring us in the future. So the two sources that I will focus on for this talk will be later, this GW150914. This is the first gravitational wave detection from a binary that is consistent with a binary black hole merger. And this GW170817, which is the first binary neutron star detection. And so if you've seen this plot before, the x-axis has absolutely no meaning. It's only the y-axis that has meaning, and it just shows the masses of the objects. So for example, if you focus here on GW150914, there's one black hole that has a mass of 29 solar masses, and another black hole that has a mass of 36 solar masses, and they merge and they form a black hole that has about 60 solar masses. So that's how you read this plot. And this is what we now have from 03. Interestingly, all black holes shrink in size. Of course, if they want to be able to fit everything in one slide, they're going to have to keep doing that because there are more and more detections coming up. So the numbers are increasing, and we have of order 55 candidate systems in the 03, as I will explain shortly. And perhaps the most, well, let me just say, here what the summary of this third observing run is, which ended early because of the COVID pandemic. So first, before I tell you what about the sources are, what the candidates are, let me just explain how LIGO classifies these sources. First, if an object has a mass, if both objects have mass between 1 and 3 solar masses, then they classify that as a binary neutron star, which is not really solid, but this is like for the first alert that they send out, this is what they do. So it's like if it's between 1 and 3 for both stars, then that's a binary neutron star. If any of the two stars is in between 3 and 5 solar masses, that's called a mass gap object. And that's because we don't know how to form through astrophysics neutron stars or black holes that are in between 3 and 5 solar masses. If it is between 5 and greater than 5 solar masses for the more massive object, because M1 here, I should have mentioned, is the more massive object, the primary, and M2 the secondary, then this would be classified as a neutron star black hole as long as the secondary is less than 3 solar masses. And then if both objects are both primary, the primary and the secondary are greater than 5 solar masses, that's called a binary black hole. And so here's the summary of 03. There's 7 binary neutron star candidates, 7 binary black hole neutron star candidates, 4 mass gap candidates, 37 binary black holes, and 1 burst. So this is the classification. Only few of these have already been made public. I mean, there's published data and published analysis on what they are, and most of them have not been made. The analysis has not been made public yet. But perhaps the most important thing is that we have 0 confirmed electromagnetic counterparts for any of these things, unlike what happened in 02, which is why I'll be focusing on the observing round 2 for this talk. But before I do that, let me just say that I guess O3, the third observing run, has already furnished a few tantalizing detections. And this is the detection of GW190521, which is the most massive binary black hole that has been detected so far. Both of the black holes that merged and formed this behemoth of 150 solar mass black hole, they are in what is known as the pair instability gap. So if a star has a certain mass range, when it collapses, it will form a black hole. But above a certain mass, it will not collapse and form a black hole. It will just be blown apart completely. And so these black holes are in have masses that cannot be formed by standard conventional stellar evolution. And so this is why these two black holes are a tantalizing detection, because one of them has definitely more than 80 solar masses and the other one is between 50 and 60 solar masses, something like that. So this is a puzzle for evolution, stellar evolution, and how these big black holes form. The second tantalizing detection is this one here, which involves this object which has 2.5 solar masses and a 22 solar mass black hole. And this is GW190814. This is interesting because one of the objects has 2.5 solar masses, so it literally is in what we would know as the mass gap. So we don't know whether this is a neutron star or it's a black hole. So there's been a lot of hypotheses, there's been a lot of papers that have been published already about what this might be. But the biggest, I guess, puzzle is that how do you form a binary that has a mass asymmetry as big as this one? Because the mass ratio is about 9-to-1 here. So how do you form if it is a neutron star here, how do you form a black hole neutron star with that mass ratio? Or how do you form a black hole binary if this little object down here is a black hole? How do you form a black hole binary that has this big mass asymmetry? So these are the opening questions for that, the open questions for that. And then finally, we have the object GW190425, which was classified as a binary neutron star. And this is interesting because it's the most massive binary neutron star that has been found. Obviously, we have only two so far. But the combined mass is 3.4 solar masses, which is far larger than any binary neutron star in our own galaxy. And so that also challenges formation scenario for these binary neutron stars. So in my opinion, these are the most interesting detections that O3 has brought so far. And of course, there are more to be published and we'll find out, I guess, in the next few months. All right, so this was the introductory part of my talk. So I will have also some background material thrown in for the second part of my talk, which is going to be about probing the neutron star equation of state. In other words, probing nuclear physics with binary neutron stars. And hopefully, if I get to the last part, which is going to be probing U1 charge and modified gravity with binary black holes. All right, so let me now tell you what are the important facts about the first binary neutron star detection, which is the event GW170817. So first of all, the gravitational wave detection showed us that there's, I think there is something in the chat or not. Oh, okay, everything's fine. All right, so some facts about GW170817. The masses from the gravitational wave parameter estimation were deemed to be 1.36 to 1.6 solar masses for the primary and 1.17 to 1.36 solar masses for the secondary. The event was seen by over 70 telescopes that were observing light on the ground and in space. 1.7 seconds after the peak gravitational wave amplitude, a gamma ray burst was also detected. And that 1.7 second difference, if you spread it out in the over 50 megaparsecs, which is where this binary neutron star was detected. Here's the optical image of the galaxy that contained that binary neutron star merger. If you spread that 1.7 seconds over a distance of 50 megaparsecs, then you can say with certainty that the speed of gravitational waves is the same as the speed of light to within 1 part of 10 to the 15. So that's the first confirmation that gravitational waves travel at the speed of light. Well, I would say experimental with light uh, uh, confirmation. And then within half a day, an optical electromagnetic signal was also detected that is known as a kilonova, and that was actually predicted early in the 90s that it would accompany such binary neutron star mergers. So here's the full, what we call now multi-messenger picture. We have the gravitational wave signal. This is the frequency of the wave, how the gravitational wave evolves as a frequency. This is the optical image where you can see this little square here, which shows the explosion, this kilonova. And down here we have the Fermi satellite gamma ray burst that was detected. And of course, it was confirmed by other satellites as well. So this was really a gold mine of opportunity, and there's I don't know, hundreds of papers maybe that have been published since 2017 on this event alone. All right, so I mentioned that there was a gamma ray burst that came from that. So that's something that I've worked on simulating for quite some time now. So let's try to see a movie of what this event might have looked like as simulated in a computer using solving the Einstein equations, solving the equations of hydrodynamics, and including magnetic fields. And I will explain where things come in the different stages, essentially where the kilonovae come and where the gamma ray burst comes from. All right, so first we have the 2 neutron stars, they in spiral. Obviously, that's where the gravitational wave comes from the in spiral phase that we detected. And then you'll see that what happens during merger, as you can see here, these spiral arms develop, which are actually flung out, and they fly at almost nearly about a third of the speed of light, and they become completely unbound as this remnant evolves. And so there's matter that is being flung out. This matter that is being expelled to infinity because it becomes unbound is the matter that gives rise to the kilonova, this optical signal that we detected after the merger. And I will explain shortly how that is generated. But now, soon after the stars merge, they collapse and form a black hole. But that black hole is surrounded by an accretion disk, which has quite a lot of matter. And it has also magnetic fields. And it's known that when we have interaction of magnetic fields with a horizon and a black hole, obviously, then we can launch jets. But now this is a self-consistent simulation that starts with the magnetic fields in the neutron stars to begin with, forms the black hole, and shows how a jet emanates from this system. So what you'll see now is this classical barber pole structure of a collimated magnetic field, a large-scale magnetic field that develops. And what happens is that the magnetic field lines are being coiled up, and then they create tension, and this tension just wants to just break away. And then what happens is that the magnetic fields just push matter away, and it just make it propagate out at very, very high speeds. So this is really the onset of a gamma ray burst, as is demonstrated here. So this is the event that was first detected 1.7 seconds after the merger. So first we saw the gamma ray burst, which is shown here. And now you'll see the arrows which indicate the velocity of the flow that is being outward directed. And it's down here is about half of the speed of light, but later on it's expected to be accelerated at very, very high speeds, close to the speed of light.
Vasily,
Yes.
Nikos Kilafis, in this simulation, was it assumed that the magnetic moments of the 2 neutron stars are parallel?
Yes. Yes.
Because otherwise it's a mess, yeah? Or
no, a simulation
create then a nice poloidal magnetic field.
Well, I mean, in general, what happens here is that it's a mess, as you can see here. In fact, what happens after merger? So the structure of the magnetic field after merger is primarily toroidal. So you have very, very little poloidal field because of the matter just being wound around, and then a lot of it collapsing and going into the black hole. So really, most of the magnetic field is in toroidal form. There's very, very little poloidal. And then what happens is that the magnetorotational instability kicks in, and it creates a colloidal magnetic field that when you accrete, you can generate this large-scale colloidal structure that emerges from the system. So it's really a combination of things. It's the magnetorotational instability that amplifies the magnetic field that is in the disk, the accretion of that onto the black hole, the motion of the matter then that stretches the magnetic field lines and creates this barber pole structure. Now, you're definitely hitting a right point that if you have a zero net colloidal magnetic flux to begin with, then it would be very, very difficult to get a jet out of the simulation. So you can have them misaligned, but if they were completely, let's say, into the orbital plane, then it's very, very difficult to get a jet. So that's a good point.
Okay, thank you.
Okay. All right. Oops. So what is this kilonova that I mentioned? As I showed you, there's matter that is being flung out. And so here what these color density plots demonstrate, this is the XZ slice of the remnant. And this is on the orbital plane, on the equatorial plane of the binary. Anything that is not purple is matter that is being ejected and goes to infinity. That's unbound. So all this gray matter that you see here just escapes and goes to infinity. So what happens is that this ejecta is a neutron-rich matter. And so as it expands, what happens is that this ejecta decompresses. And then since it's neutron-rich, there's rapid neutron capture on seed nuclei, which is known as R-process nucleosynthesis in nuclear astrophysics. And this very, very neutron-rich environment creates very heavy elements. But these elements, when they first form, are radioactive. So obviously they will decay, and this will heat the ejecta. But as time goes by, of course, the first form of these gamma ray of the radioactive heating is in the form of gamma rays, which of course thermalize because they're trapped in this cocoon of matter as it expands. And then as it keeps expanding, of course, it cools down and the thermalization process continues. So the photons become obviously cooler and cooler and cooler. And then when eventually the density becomes low enough, then the photons finally escape from this matter that they're trapped in, and a signal that is optical to infrared emerges from this event. And so this is what gives rise, a couple of days after the event, after the merger takes place, that's what gives rise to what we know as a kilonova. But that's the basic physics, the basic nuclear physics that describes these kilonovae. And calculations to explain this kilonovae suggest that about 0.025 to 0.05 solar masses were ejected in this GW170817 event. And they formed elements heavier than iron. And about a Jupiter mass of gold was formed in the event. And binary neutron star mergers, therefore, have long been hypothesized to be sites of heavy element formation like neutron supernovae. And this was the first confirmation, or the first, well, it's not direct evidence, but indirect evidence that indeed these binary neutron star mergers form heavy elements. And that's definitely one site where these heavy elements come from. So that's an important astrophysical problem that has been tackled with just one event. All right, so now a few open questions. As I mentioned, we would like to do some fundamental physics with these events. So we are going to make one assumption here, that we're going to have two matter companions. And that's because this event can be also explained in principle with a black hole and a neutron star. But of course, no one knows how to form a black hole that is less than 2 solar masses, and therefore it's quite unlikely that a black hole was involved. So the most plausible scenario is that we had 2 neutron stars or 2 matter companions. And so one important question then is, what was the fate of this remnant? What happened after the neutron stars collided? And that is important because it will help us place constraints on the equation of state from a combination of gravitational wave and electromagnetic wave perspective. And then a final question that I'm going to ask is, because everybody focuses on hadronic equations of state or hadronic matter, so neutron stars that are made primarily of hadrons, but there are also theories where neutron stars are not made only of hadrons, but they're made of a soup of hadrons and quarks. And so I'm also going to ask how these hadron-quark equations of state modify the story. So we'll try to tackle these questions one by one. But before we get to that, let me introduce some definitions, which you may have heard of, but I'd like for everyone to just understand what these things are, because I'm going to be using them for the rest of the talk. So I'm going to define what supermassive and hypermassive neutron stars are. So first, let's consider a neutron star that is non-spinning, as shown here. And obviously, neutron stars are orange. And general relativity predicts that a neutron star that is non-spinning, you cannot have an arbitrary mass. So if you keep piling mass on top of that neutron star, it will eventually reach a limit beyond which, if you pile up a little bit more mass, it will collapse and form a black hole. So this limiting mass is known as the Tolman-Oppenheimer-Volkoff limit, or the TOV limit. So this is for non-spinning neutron stars. Now let's imagine that we spin up the star. Obviously, because of the centrifugal barrier, the additional centrifugal support, we can pile more mass onto the neutron star. And we can consider now that we are spinning the neutron star with maximal uniform rotation. So I'm not considering that there's differential rotation, that is, different parts of the neutron star rotate at different frequencies, but they rotate all at the same frequency. So that's what we mean by uniform rotation, and it's maximal, which means that if you try to spin it up a little bit further, then particles at the equator of the star will become unbound. So this would be called the Kepler limit. And so these maximally uniform rotating stars also have a maximum mass. And this maximum mass for maximally uniformly rotating stars is called the supermassive limit. Okay. So now these two limits are all we need in order to define what is a supermassive and a hypermassive neutron star. So a supermassive neutron star is a neutron star that has mass m greater than the maximum non-spinning mass, but less than the maximum mass that can be supported by maximal uniform rotation. Okay, so if the mass is greater than the TOV limit and less than the supermassive limit, that's what we call a supermassive neutron star. A hypermassive neutron star is one whose mass is greater than the supermassive limit. So you can, in principle, build configurations that have more mass than this maximally uniform rotation, but this can happen only if these neutron stars are differentially rotating. Okay, so hypermassive neutron stars are differentially rotating, and they're also transient objects because differential rotation is not something that can be sustained. For example, if you have magnetic fields, they will break the differential rotation and they will make the star uniformly rotating. And since you have more mass than the supermassive limit, it will collapse and form a black hole. I should also point out that even supermassive neutron stars are transient. And that's because neutron stars spin down, as we know. So even if we have a star that has more mass than the TOV limit, but it's spinning down with time, it will reach a point where it will be very, very slowly rotating. So it will be practically non-spinning. And since the mass is going to be greater than the TOV limit, it will collapse and form a black hole. So both supermassive and hypermassive neutron stars are transient. They're not going to live forever. But typically, supermassive neutron stars survive for much, much longer times. They survive on the spin-down time scale of the remnant, whereas hypermassive neutron stars tend to survive for much less time. So this is going to be important for understanding the next parts, the next question. What was the fate of the 1708-17 remnant? All right, so now I'm going to summarize in one slide over a decade of numerical relativity simulations, but this is really the story that we know, what happens after two neutron stars merge. So really the quantity that determines what will happen is the total mass of the binary. It turns out that there is a threshold mass, m thresh, such that if the binary mass is greater than the threshold mass if the total binary mass is greater than this threshold mass, there's prompt black hole formation. If the total mass is less than this threshold mass, then there's two possibilities. If the total mass is less than the supermassive limit, then it will form a supermassive neutron star. If the total mass is greater than the supermassive limit, it will form a hypermassive neutron star, which is the definition essentially that I mentioned for the supermassive and the hypermassive neutron stars. But hypermassive neutron stars, as I mentioned, are objects that are transient, and so this leads to delayed collapse. And so it will form a black hole with a torus that will eventually give rise to a jet. So let's try to analyze now what happened, what we observed with 1708-17, and which one of these possible scenarios are plausible, or the most plausible. So first, if we consider that the binary had more than the threshold mass for prompt collapse, what numerical relativity simulations have demonstrated is that this prompt collapse has too little ejecta. So therefore, we wouldn't have a detectable kilonova. Moreover, what I've demonstrated with my colleagues is that in these cases, there's no magnetic field amplification because there's a tiny amount of disk also left outside. There's not enough left to be able to generate jets. And so we wouldn't even have a gamma ray burst. So really, this scenario appears to be incompatible with 1708-17. Which means that the total mass of the binary would have to be greater than the threshold mass for prompt collapse. Now, let's consider the delayed collapse scenario, where the total mass of the binary is less than the threshold mass, and the total mass is greater than the supermassive limit, which leads to this black hole torus eventually formation that I mentioned. Now, because of the disk and the ejecta, it turns out that there's the right amount of ejecta that can be generated. Several authors have actually pointed that out. And I have demonstrated with colleagues that this delayed collapse scenario is successful in generating these jets. And so this was the first result in 2016, where we demonstrated how the delayed collapse scenario can lead to jets. What about the long-lived neutron star scenario, or the supermassive neutron star scenario? If, again, the total mass is less than the threshold mass, but the total mass is less than the supermassive limit, the supermassive neutron star is going to survive with magnetic fields that are of order 10 to the 15 Gauss at the pole of the neutron star. It's going to survive for about a few thousand seconds before it slows down enough to collapse and form a black hole. But this scenario is really what is used to explain a class of gamma ray bursts that have an extended X-ray emission. And so this was not observed. We didn't observe any extended X-ray emission from 1708-17. Moreover, recent papers have demonstrated that these scenarios cannot really generate short gamma ray burst compatible jets. So there's several arguments that can be made that this was also not compatible with 1708-17. And so really the most plausible scenario for 1708-17 accepted by the community is that it actually is the delayed collapse scenario. And this leads to two constraints. The total mass of the binary is less than the threshold mass for prompt collapse, and the total mass of the binary is greater than the supermassive limit. So these two now can be used to place constraints on the equation of state. So let's see how that can be done. So if the total mass has to be less than the threshold mass, the total mass from the gravitational wave observation was estimated to be 2.7 solar masses. So the threshold mass for prompt collapse then has to be greater than 2.7 solar masses. And interestingly, in 2013, Boswan, Baumgart, and Janka found that this threshold mass for prompt collapse for at least a good range of equations of state follows a universal relation that if you divide this threshold mass by the maximum TOV limit mass, then for all equations of state, these relations hold, where R1.6 is the radius of a 1.6 solar mass star, and R max is the maximum mass configuration, the maximum unrotating mass configuration radius. So these expressions were then used by Boswan, Janka, Just, and Nikos Stergioulas, who may be here, I'm not sure, to place a constraint on the radius of a neutron star. So let me just go through the argument. It's very, very simple. So this expression here, if you make a plot on the threshold mass versus maximum mass plane, it becomes pretty much a expression where you can draw contours of constant radius at 1.6 solar masses. So since the threshold mass has to be greater than 2.7, which was the 1708-17 total mass for the binary, this means that everything on this plane has to lie above this line here. So we're constrained on this part of the plane. And then Boswan, Just, Janka, and Stergioulas found that there's also another empirical relation that the maximum mass in units where the speed of light and the gravitational wave, the gravitational constant are equal to 1, has to be less than 1 r1.6 divided by 3.1. And so this is this part here that is cut off. So really the plane that is allowed is here. So now you can start drawing contours of constant radius. As you can see here, this is for a radius of 12 kilometers. This is for a radius of 11 kilometers. And finally, if you draw something like for a radius of about 10.3 kilometers, you'll see that you're not falling into this part of this space anymore. And so this places a constraint that the radius has to be greater than 10.6 kilometers, the radius of a 1.6 solar mass star. And similarly, the radius of a maximum non-rotating configuration, maximum mass neutron star non-rotating configuration, has to be greater than 9.6 kilometers. So these are important because then we can use them to place constraints on the actual equation of state. But before I discuss that, let's talk about the other part of the constraint, that the supermassive limit now has to be less than 2.7 solar masses, so that we don't form a long-lived neutron star after the remnant forms. So this was used in conjunction with something that people call a universal relation, that for any maximally rotating neutron star, the maximum mass you can support is about 20% larger than the maximum non-rotating neutron star mass. And so then if you combine that with the fact that the supermassive limit has to be less than the total mass of 170817, that means that the maximum mass of a non-rotating configuration has to be less than 2.32 solar masses. So again, this is useful because, as I'll show shortly, it can be used to place a constraint on the equation of state. But before I do that, let me explain how hybrid hadron quark equations of state modify this story. And what are these hybrid hadron quark equations of state? So these are equations of state that support a phase transition between hadronic matter and quark matter. So on a pressure versus energy density plot, they would look like this. There's a pressure increase, and then there's a jump where pressure is constant, and then we have quark matter forming up in this branch. And so these stars are not just hadronic, they're not made primarily of neutrons and protons, but they have a hadronic shell and then a quark core that is very well separated. The two phases are separated as shown here in this cartoon here. And so if you build configurations of mass versus radius for these kinds of equations of state, so this would be a mostly hadronic part, this red curve that would correspond to this equation of state. But then when you have a very large jump of constant pressure across energy density, what happens is that you can break off this branch and create a stable branch of neutron stars that is shown here. So these are stable neutron stars up until this point. Then there will be another branch of unstable neutron stars, that is this part here, that is going down as I go left. And then there's a branch of hybrid quark neutron stars that form. These are called the hybrid stars. And these were discovered very early on by Glendening and Kettner, and these equations of state were discussed even by Gerlach, the known Gerlach from the Stern-Gerlach experiment in '68. And so then the next question is, how do these fit into the picture, and can they explain 170817 from a gravitational wave perspective? So that's an analysis I did with Ken Yagi and some collaborators and nuclear physicists over in Europe. Since I'm kind of running out of time, so I'm going to skip this tidal deformability explanation, but please feel free to ask me what a tidal deformability is. But what LIGO did is that it published these contours of the tidal deformability of the two objects, lambda 1 and lambda 2. So this tidal deformability is a measure of how deformable an object is when it's subjected to a tidal field. And when it's subjected to a tidal field, it deforms, and therefore it creates a quadrupole moment. And a quadrupole moment is what's really necessary to change the gravitational wave structure. And then it can leave an imprint on the gravitational wave. So LIGO really published these contours for lambda 1 and lambda 2 for each of the two objects. And if we use a purely hadronic equation of state, as shown here, then this would be this red curve that corresponds to this plot. So it would satisfy the constraints that are set. But if you have a phase transition that allows one of the two neutron stars to become softer, for the equation of state to become softer, and so the neutron star becomes more compact, that's what when you don't have a lot of pressure, what happens. So you would fall on this branch here on this tidal deformability that we can compute. And so this would be a hybrid hybrid star neutron star binary. So one of the stars would be a neutron star, the other star would be a hybrid star. And there was an analysis of how much more likely this is compared to a double neutron star binary. And this analysis ran by Essig, Landry, and Holtz found that indeed these hybrid stars, neutron star binaries, are actually favored by 170817. And so then if they're favored, then one question one can ask is, how does the universality of this supermassive and maximum mass for the TOV stars hold? Is it true for these hybrid equations of state? So that's something I looked at with my students, Botola, Espino, and Nguyen. And this shows the ratio of this maximum mass of a rotating configuration divided by the maximum mass of a non-rotating configuration, as shown here, for various values of the angular momentum, all the way to the maximum possible angular momentum value you can have. And so really, this equation here, the supramass being 1.2 times the maximum mass, would be just this end here, these points, as you can see. And it's clear from this endpoint on this plot that this expression between the ratio of the supermassive to the maximum mass configuration is actually between 1.15 and 1.31, which means that using a single value for this ratio is not appropriate. In other words, it's not a universal relation. And so anybody who uses really this to place a constraint in the equation of state is not a solid way to place a constraint on the equation of state. All right, so now I'm going to take 2 more minutes to finish this up and explain what you can do to do better than this. So instead of using just a few equations of state to find some universal relation, which is what others have done so far, what one can do is you can use a Monte Carlo approach to generate randomly nuclear equations of state in a model-independent way. So this is work that it's in preparation right now with a group of nuclear physicists in Finland, and Eva Katerini, which is a student at the Aristotle University, Thessaloniki, and myself. And so what we do is we interpolate equations of state between a low density regime that we know the equation of state works, and a high density regime where perturbative QCD, quantum chromodynamics, works. And then the interpolation between the two regimes is a piecewise linear in the sound speed squared versus the chemical potential. And from that, we build the equation of state, and then we invert and we find what's the pressure versus the energy density and everything that we need. We generate 1.5 million equations of state that satisfy all known experimental and theoretical nuclear physics constraints. And we single out only those that can support a TOV limit mass of 1.97 solar masses or more. And that's because we know that there exists a neutron star in our galaxy that has a mass of 1.97 solar masses or more. All right, so then what we can do is we can impose the tidal deformability constraint. We can generate trial binaries for each of these equations of state that are consistent with the 170817 parameter estimation. And we can impose the LIGO-Virgo tidal deformability constraint only. And then when you do that, this is the mass versus radius plane that arises from these equations of state. So these equations of state these maps here are color-coded with the maximum sound speed that is reached in the equation of state. And the lower sound speed equations of state are plotted on top of the higher sound speed equations of state, as is shown here in this image. So it doesn't mean that the yellow part doesn't cover this part here. It just covers all this space. We just plot on top of that the lower sound speed equations of state. And so you can see that if you don't impose the tidal deformability constraint, you can actually support up to about 3 solar masses for these stars. And this is the plane of the pressure versus energy density. If you are not familiar with energy density in mega electron volts per Fermi cube, you can look at the top panel here, the top line, which is the nuclear saturation density, which is 2.7 10 to the 14 grams per cubic centimeter. So this is 1 times the nuclear saturation density, 10 times the nuclear saturation, and 100 times. Okay, so this is really the plane. And now what if we impose, in addition to the tidal deformability constraint, that this remnant had to be a supermassive the mass of the binary had to be greater than the supermassive limit for that particular equation of state that we analyze, then what happens is that all this branch of higher, stiffer equations of state disappears from the mass radius plane. We can in fact place a very tight constraint of 2.2 solar masses. That's the tightest constraint that has been placed so far. And interestingly, for in the pressure versus energy density plane, we can exclude the very stiff equations of state up here, up to about 10 times the nuclear saturation density. So typically, densities in neutron stars reach about up to 10 times the nuclear saturation density. So it's really this part of the plot that we're interested in. And just by doing this analysis, we can remove a big part of this parameter space that is allowed. So nuclear physicists now can try to get their favorite models and see how they can fit an equation of state from basic principles into this plane that has been constrained with this particular process that we are working on right now. All right, so since I'm out of time, I'm gonna skip the next part and I'm gonna go straight to my conclusions. This is some work on charge that I've been doing lately with one of my students, Gabriela Bozzola, and we were able to constrain charge, but not electric charge also, but multiple different types of charge. And I'll just go directly to my conclusions. And tell you that numerical relativity is very important for the success of the multi-messenger astronomy program. We've already, collectively as a community, we've been able to place fast constraints on the nuclear equation of state. And now we have a very, very tight constraint on the maximum mass of a non-rotating star of 2.2 solar masses under the scenario that I, of course, described. We also have first constraints on black hole U1 charge. When you hear U1, you can think of just the standard electromagnetic vector potential that has been placed, and the ratio of Q to the charge of a black hole to the mass of the black hole has to be less than 0.4. And this places the tightest constraint on the coupling constant of a tensor vector theory of gravity that Moffat proposed in 2006. So I'll stop here and I'll thank you for your time. Sorry I went over, and I'll take questions.
Thank you very much, Vasilis. Questions for Vasilis?
Hello.
Hello.
I would like to ask about the O3 and O2 findings at the start of your presentation.
Yeah.
So I don't know a lot about this, but from what I saw in your diagram, there's an abundance of binary systems between the 1 and 2 range, and we see that again in the
here.
Yeah, and we see another abundance between the 20 and the 80 range, but not so many binary systems between the 2 to 5 range. And
yep.
I would like to ask, why is that?
Yeah, so I didn't explain everything on these plots. So first of all, the yellow dots that you see down here, they're mostly neutron stars that have been detected using electromagnetic waves.
Okay.
So not gravitational waves. The only gravitational wave neutron stars is this one. Let me maximize.
So the gap
so the only binary neutron stars that have been detected with gravitational waves are 2. So it's this one here and this one here. So these are all, the other ones are all from electromagnetic observations. The purple disks that you see here are black holes that have been found through electromagnetic observations as well.
Okay.
And all the blue disks are the black hole binaries that LIGO and Virgo have detected using gravitational waves. So if you recall, I was mentioning that there's a mass gap that LIGO classifies here, objects based on a mass gap between 3 and 5 solar masses. And so this mass gap is precisely what is shown on this plot here. So the lack of objects between 2 and 5 solar masses is what we call the mass gap. We don't detect either binary black holes or neutron stars in that range. And so that really it's an observational well, not constraint, but it's an observational fact. We are not detecting anything in that range, with the exception, of course, of a couple of objects, as I mentioned here. So this one here, which could be a black hole neutron star or a black hole binary. So this is the first object for which we have a measurement that it is in this 2 to 5 mass range. But there's a lack of objects, and we don't really understand.
Oh, so it's an open problem.
Yeah.
Is
So
this
that's the mass gap problem.
Oh, it's called the mass gap problem. Okay. Thank you very much. And it was a very nice talk. Thank you.
Sure.
Okay, there are a couple of more questions. The first one by Mr. Antonios Nathanael.
Yes. Hi, Vasily. Thank you for the really nice talk. So the question is about the upper bound in the Amtov maximum mass. You set an upper bound of 2.2. There are several groups that have put 2.17, 2.3, 2.32. How do you get there, and why this is the correct and not the other, if you can comment?
Well, first of all, the 2.17 that you mentioned, it comes from the uncertainty in the range, right? So it's not really a solid like 2.17. There's an uncertainty range, and that's one thing that should. So if you really want to say what's the most conservative bound, it's actually greater than that. So, and the ones that I'm aware of, at least, and you can correct me, they are based on a universal relation that I hope I made a good case that it's not a universal relation. So, so at least there's some variation in that universal relation. And so instead of assuming any universal relations in the approach that I mentioned, instead of using any ranges in uncertainties of anything that have to do with a mass range that is determined by the LIGO observation. And I should have also said that there is an inherent assumption that the result depends on the analysis that LIGO did based on the low spin priors, right? So I'm not including any high spin prior results, but if we include high spin priors, it would change the results of anybody else anyway. So it's not just that it would affect the result that I'm mentioning here. And so I don't consider any uncertainties in any universal relations. I don't consider the mass range for the total mass that LIGO published. I'm just taking the tidal deformability in the analysis, and I'm generating within the 90% confidence intervals primaries that LIGO publishes, because that's really what is the most important thing. And then the limit is also conservative, because I'm not even considering that there's ejected mass in this case, in this analysis that I perform. And so the 2.2 solar mass limit is a conservative limit in this case, in this whole analysis. When we generate these random equations of state, we populate the entire space of pressure versus energy density, if you want to say that is consistent with any nuclear physics constraints that we know from theory and experiment. And that just pops out in the analysis. We don't consider you don't even need to consider any uncertainties other than what is the mass range that LIGO publishes for the primary. Then from the primary, in the extremely tight constraint on the tidal deformability, the binary tidal deformability I should have mentioned, we compute what is the mass of the secondary. And then from that, all you need to apply is that the remnant had to have a mass that is greater than the supermassive limit. And then that just pops out from the complete analysis over there. There's no uncertainty in that conservative limit. It's just the upper bound on the limit for the maximum mass of a TOV star. Whereas the other studies that you mentioned have an uncertainty because they use the maximum mass that LIGO publishes, which is not what we do here.
And there is another question by Mr. Panayotis Yosif.
Mm-hmm.
Yes. First of all, thank you for your nice talk. I was wondering, you mentioned the possibility of a phase transition in regard to the equation of state for high density matter. And I was wondering, how is a possible phase transition going to to affect the gravitational wave spectrum in the post-merger phase? I mean, we expect there will be a F peak and a fundamental mode from the quadrupole L equals 2, and how is this going to affect in regard to assuming hadronic matter or phase transition situation?
Yeah, so that's a very good question. I would say it's an active topic of research right now. So there are a few groups that have performed simulations with equations of state that have these phase transitions. I don't know, maybe Antonis Nathanael, who gave this previous question, he might have been involved in these simulations, I don't remember. But I know that the group, the Rizzola group in Frankfurt, has actually done some work in that. And then there's another group in Germany that has also done some work in that. So it really depends on what is the mass and whether the mass of the binary is high enough to achieve these high densities in the interior of the neutron star such that you go through the phase transition, first of all. So if you're sufficiently low mass and the density doesn't ever increase enough to cross the phase transition threshold density, then you're not going to see anything different between a equation of state that has this phase transition or an equation of state that doesn't have this phase transition. So if you are sufficiently massive and you form a hypermassive neutron star or a supermassive neutron star that is sufficiently massive to cross this phase transition, people have shown that you have some very, very wild spikes, and these seem to shift, I think, what you call the F peak and anything else. But it's also very interesting because as the remnant oscillates, it can actually go in and out of the phase transition. And this can also change the fundamental mode at which the remnant can oscillate. So, you know, it's not, I would say that it's not clear right now how this works. Also, I know there's been some work by Bauswein and collaborators on using these kinds of equations of state, but it wasn't entirely, I would have to check with read the papers more carefully. It wasn't entirely clear to me that there was such a sharp, with a big jump in density to allow the formation of hybrid stars to emerge at the same time. So, you know, the bottom line, I guess, is that it definitely is going to leave an imprint that is probably going to be unique to these kinds of equations of state. But it will depend on the mass and where the phase transition threshold density is, because if it's high enough, it may never be achieved in these configurations. So it's still open, and people are really working on this. So it's not a done deal yet.
Okay, thank you.
Yeah.
Okay, there's another question by Jason Spiromilio.
Yeah, hi, lovely talk. You, on this slide that you have up, you focused on the kilonova, which is fascinating. And then you did mention the two other ones that were bizarre. And I have a couple of questions. One is on the mass ratio, the previous slide you had.
I think it's the next one that you were mentioning.
Well, it's okay. It's on both. Yeah, exactly. Okay. So on the 1908-14, and there's plenty of objects that have bizarre, strong mass ratios. Is the problem that you can't get them to merge? And in that case, what's the limit on it being a triple? And on the 1905-21, as we can see from LIGO, there's, the universe is quite happily making 80 solar mass black holes. It just makes them not through a single star. So is that a lifetime problem, that there's not enough time to actually make them and merge them?
No, I don't think it's a lifetime problem. Well, I guess it depends on what one means. Well, you asked two different things. So, or you asked, I guess, a similar question connecting two different objects. So for these two stars, for these objects, for these very massive stellar mass black holes, the issue is how, if you assume that they formed from a single progenitor. not that there was a dynamical formation. Let's say that these two black holes merged. Sorry, that these two black holes formed as a second generation of black holes.
That's sorry to interrupt. That was the question. I mean, why make that assumption? I mean, if you don't.
Yeah, so it's a matter of rates. So it's not clear whether you have enough mergers for a single black hole to be able to do that. So it does become a lifetime issue, as you mentioned, for these. If you go down the avenue of saying, oh, this might have been in a globular cluster where you have multiple generations of binary black hole mergers, then there's some capture, and then you form these bigger black holes. There has been some work by the Fred Razio group that I'm familiar with. There may be other works that have been done that show that it is possible if you don't consider a single progenitor star that forms these black holes, that it can happen. But it's not clear to me whether the rates are high enough to be able to say, okay, you know, what's the probability that we would have observed this one event. So I think the story will become clearer in the future when we have hopefully more detections of this. So this could have been one lucky event. And indeed, if it's just one-off, it can be explained easily by multiple generation black holes that form from in a globular cluster or something like that. So it is possible to explain it. I'm not saying that it's not possible. But if you assume that these black holes came from a single progenitor star, then it's that you have to overcome the problem of the pair instability supernovae.
No, that's okay. That I
yeah.
So that's
yeah. And for this object, the 1908-14, is my understanding is doesn't have to do with the lifetime. It has to do with the asymmetry in the mass ratio. And again, you could say yes, it might have been something in a globular cluster, and no one would object that. But if you assume a standard stellar evolution of a binary, then that's when people think that it's not possible to form it. So again, if you consider n-body systems, the story is different. But if you consider single progenitors that formed these stars, there was a binary star that collapsed and formed a black hole, and then collapsed and formed a neutron star, or which one ever happened first, then that's difficult to form these kinds of binaries in these scenarios.
Thank you very, very much.
Yeah.
And one last question by Nikki Lafis.
Vasily, I am aware of GR-MHD simulations that have been done in accretion disks where all these things that you discussed have been proven. Has any GR-MHD calculation been done on the neutron star case, that is together with the collapse to actually with magnetic matter and magnetic field?
Yes, that's the simulation. The movie that I showed you from the simulation that had matter, magnetic fields, but the matter description was simplified. It wasn't like a serious nuclear equation. It was a polytropic equation with
that's
index 2.
Okay.
So yeah,
that's okay. But okay. So the collapse was together with the magnetic field. So
correct. Yes.
Okay. All right. Very impressive. Very impressive.
Thank you.
Indeed, these simulations are quite impressive. So, any other questions for Vasileios Paschalidis? Okay, then let's thank him again for this very clear presentation. And
well, thank you all for the invitation.
Thank you. Have a good night.